this problem, what we're going to do is we're going to be using this rectangle. You might have seen it in a previous video. And we're going to use it to find the gravitational field. Now, here at these three corners of the rectangle are masses. I have their masses written right here. And the gravitational field, so we're starting to introduce this idea of a field, which is something that permeates space. And the reason that the way that we can detect it is when we place an object in the field, it feels a force. So we've probably said the words gravitational field at some point in our lives. And literally what we know about it is when you're in the gravitational field of the Earth, you feel pulled down to the surface of the Earth. And it's the idea is that you put your mass in the field and it feels a force down. So this expression for gravitational field, you might have noticed in your reading and in class, ends up to be really equivalent to the acceleration of gravity. So the units of g are meters per second squared. And if we used the mass of the Earth and the radius of the Earth, we would actually find that this was 9.81, which is the acceleration of gravity. In this particular example, we're using smaller masses and very small distances, but it's just a way to practice finding the gravitational field at a point and then also adding the vector sum of the individual gravitational fields so that we can find the total field present. So we're looking for the gravitational field at this point P. No, nothing is there, but we can still figure it out. And we're going to start off by drawing the gravitational field vectors on this diagram. They're going to be one for each mass. And the way the gravitational field works is that it is directed towards the mass that's causing it, which is kind of the idea that if I would put another mass in this field, it would feel attracted to mass 1, for instance. So I'm going to write G1 is going to go towards mass 1. G2 is going to go towards mass 2. And then G3 is along the line that joins point P and mass 3, and so it's at that diagonal. So now I'm going to find the magnitudes of each of those G's. Pen doesn't really want to work very well. I find that the magnitude is 1.25 times 10 to the minus 9, and that is in meters per second squared. So that is going to be G1. Let's try another color because pink isn't really working. Let's try blue. G2, we're going to use a similar expression. We're just replacing the masses and the distances for these different values. And we find that the gravitational field due to mass 2 is 1.48 times 10 to the minus 9. Again, these numbers are super small because gravity is very weak, and we have small masses and small distances. And finally, I found G3, which was 8 times 10 to the minus 10 meters per second. Now, in order to find the total gravitational field, we have to find the total x components. So we need to add the x components of these three vectors, add them up. So I have G1x plus G2x plus G3x. G1x, G1 is totally in the x direction. So I just write down that magnitude. G2, down, has no x component. G3 has an x component, that angle theta is 36.9. I'll let you do the math to figure that out. And so we would use the cosine, G3 times the cosine of that angle. And when we add those together to find my total x component, I get 1.89 times 10 to the minus 9 meters per second squared. Now I'm going to find the total y component. G1 doesn't have a y component because that was all in the x direction. But remember, G2 was strictly down, so we'll write its y component is just minus 1.48 times 10 to the minus 9. And then the y component of G3 is actually also negative, and so we'll take it, the magnitude of G3 times the sine of the 36.9. When we add all those together, we find the y component is minus 1.96 times 10 to the minus 9 meters per second squared. So we found the total x component and the total y component. G total is going to be the square root of that x squared plus that y squared. And we find a total gravitational field at that point is 2.72 times 10 to the minus 9 meters per second squared. And when we find the angle, it's 46 degrees. But when we look at our components, we have a positive x and a negative y, so that's going to be in the fourth quadrant, and so this is 46 degrees below the positive x-axis. Again, we wanted to really specify where exactly that's going to be. All right, so I hope that these examples helped, maybe give you a refresher on adding vectors and then incorporating these new definitions, like here in this we have the gravitational field.